In this video, we're going to look at some practice problems relating to the second derivative. So the first example, let's look at the population of a town given in thousands of people in different years. So our function is given by a table of values here. The question says, determine the sign of the first and the second derivative. And we're going to try to determine possible concavity. So note that a lot of the work is done here already. What we're doing is, because we can't find the exact value of the derivative, we have to estimate it given the values that we have. So if I want to estimate what the derivative value is at 1980, I can use the 2 points, 1980 and 1985, and find the average rate of change between those 2 points. That's going to be the change in the population, 15.8 thousand minus 12.7 thousand, divided by the change in the years, which is 5. If we do that calculation, we get 0.62. If you do the same for 1985, this time we use 1985 and 1990. Note that we could also use 1985 and 1980, but just to kind of keep with the same pattern. There's not one right way to estimate something. But if we do 1985 and 1990, we get 20.9 minus 15.8 divided by 5. That's going to be 1.02. And we do the same for 1990 and 1995. So these are the derivative values. And these match maybe what we can see just by looking at the table, that this function is increasing each 5 years. That means that the first derivative is positive. And we saw that for our 4 values that we found, that we have a positive derivative. And the magnitude of the derivative is telling us how much it's changing. So it changes the most around 1985 because the 1.02 is the biggest value that I found. And it changes the least in 1980 or 1995. Because I have the smallest value that I found for the derivative. So now we think about the second derivative, what's going on. We're trying to see, is the derivative increasing or decreasing? So let's look at the change between 1980 and 1985. We have that we're going from 0.62 to 1.02. So this is increasing. As we go from 1.02 to 0.14, we are decreasing, and same to 0.10. So this means that the second derivative is going to be positive at the beginning, and then it's going to be negative, which means that we are going from concave up to concave down. Determine the possible concavity. We're going from concave up to concave down. The function is always increasing, concave up to concave down. So if we had to sketch this very quickly, we have an increasing function, concave up to concave down, something like that. And of course, we could do a better graph if we look at the exact values. So next example, we have a graph instead of a table to give us our function. We have a particle is moving along a straight line. Its acceleration is 0 only once, and its distance to the right of a fixed point is given below. So what's going on is we have this particle, it's lying on the ground, or not on the ground, but think about lying on the ground, and it is just moving back and forth on the ground. We're moving right and left. And this is tracking how far we are moving away from the wall or moving away from the initial point. So we can see that we're going to start at 0, and at 5 seconds, or 5 time units, we are also going to be at 0. As we move, if this function is increasing, we are moving away from that point to the right. If we're decreasing, we're moving toward that point. So, first question, estimate when the particle is moving to the right. That is going to be when the function is increasing. So let's just kind of sketch where this is going to be. We're increasing here, increasing here. So that's going to be on the interval 0 to about 1.7 maybe. And 5 to call that 6.25. The particle is moving to the left. That means that the function is decreasing. That's going to be on this middle section here. That's going to be on the interval 1.7 to 5. Now let's think about when the acceleration is 0, negative, and positive. Let's first start talking about when the acceleration is negative. That's going to be concave down. So this function is concave down on about that interval. And there's some point where it changes from concave down to concave up. We are going to be concave up when the acceleration is positive. We'll say on that interval right there. And there is some special point right here where we switch from concave down to concave up. That's what we're going to call an inflection point. And this is where the acceleration is going to be equal to 0. If we go from negative acceleration to positive acceleration, it's like we are crossing the threshold of acceleration equal to 0. So to answer the questions, when is the acceleration negative? That's going to be on the interval 0 to about, call this maybe 3.3. It is going to be positive on 3.3 to the end of the function, which we called about 6.25. And it's going to be 0 at t equals 3.3. So we're using the shape of the graph to tell us something about the derivative and the second derivative, whether it's increasing, concave up, concave down, decreasing. So last example here, given the graph of the function, sketch the second derivative. So one way to do this is that we could sketch the derivative and then sketch the derivative of the derivative, but we're going to do it in one big swoop, just do the second derivative. So I need to figure out when is the function concave up and when is it concave down. So this function is going to be concave down On that interval right there, maybe we'll go all the way to 0. That's kind of where it changes. And on this interval. All right, so that's not precise. We're just trying to be an estimate about it. That's where it seems to be concave down, and then it switches to concave up at that point. So the green lines here are going to be concave down. That means that the second derivative is negative. This blue line here is concave up, and that's going to be that the second derivative is positive. And note that we have two special points here where the second derivative is equal to 0. Those are going to be the inflection points. And that's at 0 and 6, when the second derivative is 0. Then we see that the second derivative is going to be negative, then go to positive, and then back to negative. So it's going to be negative here, change to positive, and then go back to negative. We have something like this. It's going to look kind of like a parabola. In fact, it will be a parabolic shape for this function.